Now we will discuss the conduction in detail. Under this topic, we will see the general heat conduction equation, thermal resistance concept, resistance, network method, then critical radius of insulation, heat transfer through extended surface, extended surface, that is fins. And last, we will discuss the transient heat transfer. Now we will start with general heat conduction equation. General heat conduction equation. Consider a rectangular element of length delta x, delta y, delta z. Let us say this length is delta x, this length is delta y, this is delta z. Let us say the density of this material, of this element, is rho in kg per cubic meter, and the specific heat this material is C. C is in U per kg Kelvin. Let us say Q dot x Q dot y and Q dot z amount of heat enters at xyz. Let us say this is our coordinate system. Okay. This is x, this is y, and this is z. And we will say that Q dot x plus delta x, Q dot y plus delta y, and Q dot z plus delta z amount of heat lifts the surfaces at x plus delta x, y plus delta y, and z plus delta z surfaces after time delta t. So from first law of thermodynamics, delta Q is equal to change in internal energy plus work done by the system. Here we assume that there is no work interaction between system and surrounding. Here our system is rectangular element and surrounding. So the first law of thermodynamics reduces to heat interactions is equal to change in internal energy of the element. Okay. And since all the heat transfer takes place at constant pressure, so we can say the change in internal energy is nothing but the change in energy content of the element, and which is given as mCp delta T. Or we can say, since rho is the density of the element and its volume is delta Y delta Z, so mass can be written as rho times del X del Y del Z. Cp is nothing but C into delta T. This is our change in internal. So the rate of change of internal energy dH upon dt is nothing but limit t tending to 0 rho del x del y del z delta t upon del t. And if we apply the energy balance, energy interactions, all the energy interactions is rate of heat transfer at x, y, z minus rate of heat transfer at x plus delta x, y plus delta y, g plus delta g. We are putting a negative sign because these heats are leaving the element, and in thermodynamics we know heat added to the system is positive as the first term, and heat leaving this system is negative as it is the second case, this negative sign, plus rate of heat generation inside the element. Let us say there is a heat source inside the element which is generating E dot gen amount of energy or heat joule per meter cube second. So del q dot can be written as q dot x plus q dot y plus q dot z minus q dot x plus delta x, q dot y plus delta y minus q dot z plus delta z plus E dot gen times delta x delta y delta z. Substituting all these values, in first law of thermodynamics equation, and after a lengthy manipulation, we get del upon del x kx del t upon del y plus del upon del y ky del t upon del y plus del upon del z kz del t upon del z plus v dot gen is equal to rho c times del t upon del z. If we assume kx is equal to ky is equal to kz is equal to k, that is, material is isotropic. Isotropic means no property variation with direction. The above equation will be reduced to k upon del t upon del y, sorry, del x plus del upon del y k del t upon del y plus del upon del z k del t upon del z plus E dot gen is equal to rho c del t upon del t. This is known as the general heat conduction equation and is known as Fourier-Biot equation. Fourier-Biot heat conduction equation, also known as 3D heat conduction equation. Special cases. Good. Let us say heat conduction is taking place in a steady manner. That is, steady state heat conduction. That means temperature is not a function of time. So, in general heat conduction equation, the right hand term rho c del T upon del T will be equal to 0 and equation will reduce to del upon del x k del T upon del x plus del upon del y k del T upon del y plus del upon del z k del T upon del z plus E dot n is equal to 0. And if k is equal to constant, that is, k is not a function of temperature, then the above equation will be reduced to del 2t upon del y square del 2t upon del z square plus E dot gen upon k is equal to 0. This equation is known as Poisson's equation. if E dot gen is equal to 0, then general conduction equation will be reduced in this form. Del T square del 2T upon del G square is equal to rho C upon K del T upon del T. This is same 1 upon alpha del T upon del T. This is known as the diffusion equation, where alpha is the diffusivity, thermal diffusivity of the material, which is equal to K upon rho C. This is nothing but heat conduction upon heat storage. The value of alpha indicates how fast energy can distribute in a medium. Third case is if E dot gen is equal to 0 and heat conduction is a steady state process, that means del upon del T is equal to 0. Then the general heat conduction equation will be del T upon del x square del 2T upon del y square del 2T upon del z square is equal to 0, and this equation is known as Laplace equation. Now, the general heat conduction equation, in cylindrical coordinate system is given as 1 by r del upon del r AR del T upon del R plus 1 by R square del by del phi K del T upon del phi plus del upon del Z K del T upon del Z plus E dot gen is equal to rho C del T upon del T, where consider a cylindrical ball. This axial length represents Z, this is R, and perpendicular to the circumference, this represents phi. This is the phi direction. If we assume that there is no heat conduction in phi and z direction, then heat conduction equation will reduce in the form 1 by r del upon del r k del t upon del r plus E dot chen is equal to rho c del t upon del. This is the heat conduction equation. 1D heat conduction equation in cylindrical coordinate system. And this equation is very important. General heat conduction equation. General heat conduction equation in spherical coordinate is given by 1 by r square del upon del r k r square del t upon del r plus 1 upon r square sin square theta del upon del phi k del t upon del phi plus 1 upon r square sin theta del upon del theta k sin theta del t upon del theta plus E dot chen is rho c del t upon del. If temperature is only function of R, then del T upon del phi is equal to del T upon del theta. So, general heat conduction equation reduces to del upon del R kr square del T upon del R plus E dot chen is equal to rho c del T upon del T. This is the 1D heat conduction equation. Heat conduction equation in spherical coordinate system. If we see the 1D heat conduction equation in rectangular coordinate system, cylindrical coordinate system, and spherical coordinate system, we can write a general 1D heat conduction equation. This can be written as 1 by r to the power n is equal to del upon del r k r to the power n del t upon del r is equal to general heat conduction equation. General heat conduction equation in a spherical coordinate system. Is given as 1 by r square del upon del r kr square del t upon del r plus 1 by r square sin square theta k del t upon del phi plus 1 by r square sin theta del upon del theta k sin theta del t upon del theta plus E dot chen is equal to rho c del t upon del t. This is the general heat conduction equation in spherical coordinate system. If temperature is only a function of R, then del T upon del theta is equal to del T upon del phi is equal to 0. So the heat conduction equation reduces to K R square del T upon del R plus E dot Gen is equal to rho C del T upon del T. This is 1D heat conduction equation in spherical coordinate system. Spherical coordinate system. If we analyze the 1D heat conduction equation in spherical, cylindrical and rectangular coordinate system, then we can write 1D general heat conduction equation in general coordinate system. General coordinate system as 1 upon r to the power n del upon del r k r to the power n del t upon del r plus E dot gen is equal to rho c del t upon del t. So for rectangular coordinate system, rectangular coordinate system, n is equal to 0 and r will be equal to x. For cylindrical coordinate system, cylindrical coordinate system, n is equal to 1, and for a spherical coordinate system, spherical coordinate system, n is equal to 2. So if you remember these three conditions, you need not to remember all the three 1D heat conduction equations. You can derive it from here on.